Okay, a question about nuclei and isotopes and stuff like that. So, part A. Which two nuclei of these four have the same number of neutrons? Okay, we have uranium-234, uranium-235, plutonium-238 and americium-238. Right, what was the question again? Which two have the same number of neutrons? Okay. This number, okay, is the mass number and is the number of protons and neutrons. This is the atomic number or the proton number and is just the number of protons. So the number of neutrons, therefore, is that number minus that. So 234 minus 92 is 134 plus 8. Which is 142. Okay, so this one, uranium-234, has 142 neutrons. Right, this one, 235 minus 92 is 135 plus 8 is 143. So that has 143. Uranium-235 has 143 neutrons. 238 minus 94 is 138 plus 6 is 144 neutrons. And finally, 238 minus 95 is 138 plus 5 is 143 neutrons. Okay. Well, it's these two then, isn't it? 143 neutrons. 143 neutrons. Uranium-235 and americium-238. Which is B on the multiple choice. Okay, part B. 1. State what is meant by half-life. Okay. Commit this definition to memory for the rest of your life and just regurgitate it in the exam, okay? The half-life of an isotope is the time it takes for the radioactivity of the isotope to fall to half of its original value. Okay? Simple as that. Commit that to memory, and that's what half-life is. Just regurgitate it. Okay? Right, B part 2. Shall I write that out? I'll write that out, yes. Half-life, definition. Okay, there's no excuses for not learning it then. The time, I'm going to get it exactly right. Time taken from the radioactivity of an isotope to fall to half its original value. The time taken for the radioactivity of an isotope to fall to half its original value. Okay, learn that word for word. Right, part 2. Right, we have 925 grams of plutonium-238. 925 grams of plutonium-238. We're told that 1 gram has a power density of 0.54 watts per gram, and I'm writing it that way deliberately. Okay, we're told that the half-life is 87.7 years, and it wants the energy released per second after 263 years. Energy per second after 263 years. How on earth do we do this? It's no problem. Okay. First thing to look at is how many half-lives have we gone through after the time they're asking about. So it's 263 years, okay? So we've got 263 years, and we're told that the half-life is 87.7 years. So divide the time they've asked about by the half-life, 87.7, and that will tell you how many half-lives we've gone through. So that's the first thing. And you get 2.998 something something something. Okay, they've deliberately chosen this number because they're making life easy for us. It's almost exactly 3 half-lives, okay? Don't work with 2.998. It's 3, okay, which is nice. So, after 263 years, it's halved, the radioactivity has halved, it's halved again, and then it's halved again. Okay? Good. Right. So, if 3 half-lives have passed, we can work out how much of this is left. So, we have 925 grams. Whoops. 925 grams, okay, and 3 half-lives. So, after 1 half-life, there's half of it left. The other half has decayed. After the second half-life, there's half of that left. And after the third half-life, there's half of that left. So 925 times a half times a half times a half is how much is left after 263 years. Stick that in your calculator. It's 925 divided by 8, and you get 115.625 grams. Put that in your calculator's memory. Okay? Right. So, we now know how much we have left after 263 years. So we've used that, and that. We've just got this. I wrote it like that because look at the units. Okay? It's asking for the energy per second, which is watts. Energy per second is joules per second. The unit of energy is joule. And they've told us it's 0.54 watts per gram. Okay? So look, we have 115 point something grams, and it releases 0.54 watts per gram. So, just by looking at the units, okay, we know that if we multiply 0.54 watts per gram by something in grams, 115.625 grams, just look at the units. Grams on the bottom, grams on the top, they cancel. And whatever that is, it's going to be in terms of watts, which is what we want. So that's how we know that we have to multiply that by that, just by looking at the units. Okay? So do that. 0.54 times 115.625, and you get 62.4375 watts. Okay, now let's neaten that up. Didn't ask for any particular decimal places or significant figures, so let's be sensible. 1 decimal place seems sensible here. So that's 62.3 leaves the 4 alone, 4 watts. So that's the answer. 62.4 joules per second. A watt is a joule per second. And they wanted the energy per second. Okay? So that's it. That's a 2. Okay. Right. Final part. We are told that an americium 238 can absorb an electron. Okay, so the proton in the nucleus, right, plus the electron, which is drawn like that, turns into a neutron. Yep, that's correct. Right. Describe how absorbing an electron affects the proton number, okay, and the nucleon number. Not the neutron number, the nucleon number, okay? The nucleon number is another word or another way of describing the mass number. It's the number of protons and neutrons, okay? So the nucleon number is 238 to start off with. Okay, so describe how absorbing an electron affects the proton number. Well, inside this americium, I think that's how you say it, americium, who cares, nucleus, a proton is absorbing an electron and turning into a neutron. So the number of protons, this proton no longer exists. The number of protons has gone down by -1. Okay? What about the nucleon number? That's the number of protons and neutrons. Well, the number of protons has gone down by 1, but the number of neutrons has gone up by 1. So overall, it hasn't changed. It's changed by 0, if you like. Okay? And that's it. Okay. So, which nucleus is formed when this happens? So we started off with an americium 23895 nucleus. The proton number has gone down by 1. So whatever we're making here, it used to have 95 protons, it's now got 94, okay? And the nucleon number hasn't changed, because as we talked about, it's lost a proton, but it's gained a neutron. So it's gone -1, then +1, it hasn't changed. So that's still 238, okay? 23894, look at that, it's plutonium. And that's it. There we go. Which was, okay, multiple choice, that last one, that was C, I believe. So, there we go. Nice little question, all about nuclei and half-lives and stuff. Cheers. Oh.